thing, but just a second. Yeah. Now we represent DFT in the matrix form. Okay. So here, okay. So just the title of today's topic is matrix form representation of DFT and IDFT using Twiddle factor. Okay. So here we consider x of n as sequence of n elements and x of k also as a sequence of n elements to find n point DFT of n point sequence. X of n is nothing but our DTFT signal. X of k is our DFT signal. So we are calculating the DFT for n point sequence. Okay. So here we define the new factor. That factor is known as a Twiddle factor, and here we assign the capital W is a Twiddle factor, which is nothing but e raised to minus j 2 pi, which is nothing but a complex term. So we define a new term, that is Twiddle factor W is equal to e raised to minus j 2 pi, which is nothing but a complex term. Now we can write omega n. Suppose we are taking W as a Twiddle factor, then W suffix n, that is represented by e raised to minus j 2 pi by n. Here, just a second. Here whatever suffix n I am using, so this minus j 2 pi by capital N. Now Wn W suffix n raised to k is equal to e raised to minus j 2 pi k by n. Sk is the superscript, so it is multiplied, and n is the suffix, so it is divided. Similarly, Wn W suffix n raised to kn is equal to e raised to minus j 2 pi kn divided by n. This is how we define the Twiddle factor. For first is simple W, that is e raised to minus j 2 pi. Then W suffix n, that is nothing but e raised to minus j 2 pi by n. Then W suffix n raised to k is equal to e raised to minus j 2 pi k by n. Then W suffix n raised to kn is equal to e raised to minus j 2 pi kn divided by capital. So we represent the endpoint DFT. Now instead of this earlier factor, now we replace that with the Twiddle factor. So our equation to obtain the endpoint DFT is now represented as x of k is equal to sigma n is equal to 0 to n minus 1, small n is equal to 0 to capital N minus 1, x of n, Wn, W suffix n raised to kn, where k is nothing but 0 to n minus 1. So we can write the same thing in a matrix form or in a vector form, because this is a, when we represent this n cross 1 thing, so it represented as a whatever x of n. Here we represent this x of n as a, in the bold letters, x suffix n, which is nothing but n cross 1 input signal vector, and x of k, which is nothing but DFT of this particular sequence, endpoint DFT, which is nothing but in bold letters x of capital N, which is nothing but x of x suffix n, which is nothing but n cross 1 DFT vector, which is represented over here. Here this is small x suffix n in the bold letters is equal to x0, x1 up to xn minus 1, which is nothing but endpoint sequence. And this is nothing but the DFT of the given endpoint sequence x0, x1 up to xn minus 1. Here x is small, here x is capital. X, when we are taking in bold letters, x small, which is nothing but input signal vector, and we represent in capital X in bold letters x suffix n. This is nothing but DFT of the given sequence. Just a second. Okay, now let me represent this Twiddle factor matrix. So here we can write x of n, here whatever x of n we are, x of k we are written. Now if we represent in the Twiddle factor, which is represented as capital Xn, x suffix n in bold letters, here x of n, which is nothing but your twiddle factor matrix omega n, or not omega, but Wn into x of n. Here x is capital, which represent nothing but the DFT of given endpoint sequence. Here omega n, and here small x n means your input sequence. Here when we write this equation, just a second, let me. Here this x of n is nothing but your DFT. This small x of n is nothing but your input signal vector. Here omega n or Wn, which is nothing but twiddle vector. Okay, so here as we have seen in the previous slide, here x of n is nothing but n cross 1 vector, which is nothing but input signal vector. The size of that vector is n cross 1, which is nothing but when we write column vector, or when we write n cross 1, which is nothing but it represents one column vector. It is represent a column vector. Similarly, x of n, when we write capital X n here, which is nothing but the DFT of the signal, which is nothing again n cross 1 DFT or output signal vector, which is nothing but a again in the n cross 1 or column vector. Okay, and here whatever omega n or Wn we are written, which is nothing but represent the twiddle factor matrix. So this omega n is a twiddle factor matrix. The size of this matrix is n cross n. So here we have to obtain the DFT of the signal, which is a column vector n cross 1, input signal, which is n cross 1. So here when you, this is the size of this DFT is n cross 1. Here size of this signal is n cross 1. So to obtain x of n from given input sequence, we have to multiply it with the twiddle factor matrix. The size of that is n cross n. Okay, so when n cross n matrix is multiplied with n cross 1 column vector, the outcome is again n cross 1 column. So here Wn is nothing but n cross n twiddle factor matrix. So here this matrix is represented as Wn is equal to first column, first row, if I am taking omega n raised to 0, all columns having the same value. In the second row, first column is omega n 0, second is omega n 1, omega n 2, up to omega n raised to n minus 1. So let us discuss why we are writing omega n 0 over here for this entire row, and what are the meaning of this second row. So first we have written omega n 0. So now we come to this equation. In this equation, just a second, again let me select the pointer. Okay, here in this vector x of k is equal to sigma, just a second, is equal to sigma n is equal to 0 to n minus 1 x of n omega suffix n raised to k. So initially we are taking k is equal to 0 and small n is equal to 0. First we apply k is equal to 0. This k is equal to 0. So when we are taking k is equal to 0, k here this twiddle factor is omega suffix n raised to kn. So k multiplied with n. So as we are taking k is equal to 0, what happened? This k and n both multiplied. So this will become omega n raised to z. And here x of n. So here n is again started from n is equal to 0 to n minus 1. So when n is equal to 0, initial term is n is equal to 0. So this x of 0 omega n raised to 0. So this is what we are written over here. Omega n raised to 0. For the first position, this is nothing but the first position. At this place, you are getting omega n raised to 0. Now what about the second place? In the same row, we are going for the second column. Now we are not changing the row, same row, but second column. So in the same row, when we are continuing with the same row, means always we are taking k is equal to 0. So if k is equal to 0 and you multiply it with any value of n, always your output is 0. So here omega n raised to k into n. So here k is equal to 0 for the first row. We are taking n is equal to 0, n is equal to 1, up to n is equal to capital N minus 1. This is the length of your endpoint sequence. So always when you multiplied any value of n with the value of k at the initial is 0. So all for this entire row, what happened? Your omega and n raised to 0. So for this first row, just a second, let me discard this. Okay, for this first row, first is you are getting omega n 0, omega n 0, omega n 0 up to last. So when any value of n multiplied with k's value is equal to 0, always your outcome is omega n raised to 0. So first row represent omega n raised to 0. Okay, now we are changing this. We are taking n, k is equal to 1. So when k is equal to 1, okay, initially k is equal to 0, now k is equal to 1. So first is we are taking k is equal to 1 over here. Now n is started from value n is equal to 0 to capital N minus 1. So first n is equal to 0. So when you are taking n is equal to 0, multiplying with k is equal to 1. So again you are getting omega n raised to 0. So in the second row, first column having value omega n raised to 0. Okay, now we move to the second value. So k is equal to 1. Now second value of n, that is nothing but first we have taken n is equal to 0. Second value is n is equal to 1. So when we are taking n is equal to 1, what happened? Omega n, omega suffix n, kn, k is equal to 1, n is equal to 1. So both are 1, 1 into 1. So here you are getting omega n raised to 1. Now third value, when n is equal to 2. Now n is changing, k is fixed. So n is equal to 2. So when you are taking n is equal to 2, again you are getting it is multiplied with 1. So here omega n 2. And up to the value of k n is 0 to n minus 1. So 0 to n minus 1 means every value is now multiplied with 1. So you are getting at the last omega n raised to n minus. This is how we represent the second row. Now we move to the third row. In the third row, now we are taking k is equal to 2. Okay, now k is equal to 2. Initially n is equal to 0. So but obviously in the third column again we are getting omega n 0 because initially n is equal to 0. It multiplied with any value of k. You are getting first column of every row as a 0. Here also 0 up to at the end you are getting this also 0. Okay, now we move to the second value of n. Second value of n is 1. Now here k is equal to 2 and n is equal to 1. So what happened? Now first after first column you are getting second value 2 into 1. So that is omega n 2. So now nothing but every time k is equal to 2. So whatever values of n, that is multiplied with 2. So what happened? You are getting omega n raised to 2, omega n raised to 4, and at the last omega n raised to 2 and n minus 1. Okay. Now similarly, when you apply the last value of k, that is n minus 1. So k is equal to n minus 1. We start with the first value 0. First row is first column is 0 in the last row. And similar, and then here we are taking k is equal to n minus 1. So k is equal to n minus 1. And we are applying the another values of n, that is 2, 3, like this. So we start with the 1, 2, 3. So first value is 1. So n minus 1 multiplied with 1, that is omega suffix n, n minus 1. Second value n is equal to 2. So omega n twice of n minus 1. So this is the representation of last. Hope all of you are getting about this Twitter factor matrix. Please reply in the comment box. Otherwise, I will repeat this slide. Yes, anybody having query? Ajitha, my voice is not clear. Now I think it is clear. Please reply in the comment box. Okay. All of you clear about this Twitter factor matrix, or I need to repeat it? Anybody have any query? Okay, because this Twitter factor matrix we have to utilize for the next coming example. So it is must that you all must be clear about this trivial factor matrix representation, how we are writing this all notations. Okay, so if you have any doubt, please let me know. I can repeat. Otherwise, we will go for the next topic. Okay, it is good. All of you are getting this. So now we move to the next slide. In the trivial factor matrix, there are the two properties, mainly two properties we are discussing. We are utilizing for the solution of examples. So first is these terms are written. Prior to discuss these properties, the terms are omega n raised to 0 is equal to 1. Omega n raised to 0. Omega suffix n raised to 0 is equal to 1. Now let us discuss same thing over here. Now omega n, what we have written, omega n raised to 0 means first column. Just a second, let me erase all the ink. Okay. Here this row, first row and first column. Everywhere you are getting the term omega n raised to 0. What about the value of this term? So we move to this equation, omega n raised to 0. So when we are writing omega n raised to 0, so we are talking about this term over here. Okay. Omega n raised to kn. So here suppose I am taking this term as a 0. Omega n, the value of k into m is equal to 0. So what happened? Here e raised to minus j 2 pi kn divided by n. So here value of kn will be 0. So here we are taking the getting the term e raised to 0. Okay. So omega n raised to kn, where for the first column, for this first column and for this first row, your values are nothing but omega suffix n raised to kn. So value of kn is equal to 0. So for the solution of this, e raised to minus j 2 pi kn divided by n. So this kn term is 0. So e raised to 0. So e raised to 0 is nothing but which represent the value 1. Okay. So here we are written in short, omega n raised to 0 is equal to 1. So what happened? This first row and this first column will be replaced by 1. No need to go for the calculation of this omega n raised to 0. This is nothing but they are automatically means when we solve this equation, we can get it. The value is 1 always. So by default, we are writing 0 at the first column and 0 at the first row. Okay. Now second is when we are taking omega n raised to n, omega suffix n raised to n. So what will be the value for this? Here omega n raised to capital N. So here this term is now capital N. Okay. So this term is now capital N. So this entire term is capital N. Okay. So this n and this n will be cancelled out. This n and this n will be cancelled out. Let me repeat again, just a second. Here we have written the term as you can see over here, omega n raised to n. Okay, so omega n raised to n. So here this kn entire term is represented with the capital N. Okay, so this kn is again represented with the capital N. So when you write capital N over here, capital N over here, both will be cancelled out. So now the term remain is e raised to minus j 2 pi, e raised to minus j pi. The meaning of this is a complex term. So if we expand this, we will get the solution. So the expansion of this term is cos 2 pi minus j sine 2 pi. Cos 2 pi minus j sine 2 pi. So when you write cos 2 pi minus j sine 2 pi, the value is equal to cos 2 pi is equal to 1 minus j sine 2 pi is equal to 0. So here for this particular term, when you write this and find out the solution of complex term, just a second, forget about this. The answer is 1 only. So here answer is 1 again. So for first term, your answer is 1. Second term, omega n raised to n. omega suffix n raised to n is equal to 1 also. Now we go for the third term, omega n raised to n by 2, omega n raised to n by 2, omega suffix n raised to n by 2 means this is nothing but our midpoint. So in this, just a second. Now omega n, here this entire term is n by 2 instead of n. Now we are taking n by 2. Okay, if you are taking n by 2, this again kn is nothing but n by 2. N and cancel out, 2 will be removed, this n will be cancelled out. So now final term you are getting e raised to minus j pi. Okay, e raised to minus j pi. So omega n raised to kn. Now what we are taking, the midpoint or middle point, that is n by 2. So n by 2. So here e raised to minus j 2 pi, kn is replaced with n by 2. N will be cancelled out, this 2 will be cancelled out, and the final term remain over here is e raised to minus j 2 pi, which is nothing again a complex term. So that is cos pi minus j sin pi, cos pi minus j sin pi. So if you solve this, the answer is simple, that is minus 1. So here this term is represented as minus 1. Okay, so the three terms are available with us. Omega n raised to 0, omega suffix n raised to 0 is equal to 1, omega n, sorry, omega suffix n raised to n is equal to 1, omega suffix n raised to n by 2, that is equal to minus 1. Hope all of you clear about this. If you are clear, then we are go for the discussion of the properties. All of you clear about this discussion? Let me confirm from few of you. Okay, Kamal Kant, so Ashish Yadav. Okay, good. Just a second. Yashvi. Okay. Okay, let me ask few of you about this. Darshil Lalchandani, please unmute your mic.
Yes, sir.
Yeah, you got this.
Yes, sir.
Do you have any query?
No, sir.
Okay. Siddharth, CO18 or CO11. Siddharth, please unmute your mic.
Yes, sir.
Yeah, you got about this trivial factor and all these values.
Yes, sir. I got it.
Any query?
Not right now, sir. No.
Okay. Okay, as all of you are getting about this simple calculation, which is easy one, but as we have to utilize this in the example, I have confirmed that you are getting this or not. Okay, so as you are clear about this, let me go for the next topic. So here we are discussing the two properties of the trivial factor. First property is symmetry property of the trivial factor. So symmetry property of the trivial factor. So here we are written omega n raised to omega suffix n raised to L plus n by 2. Okay, so here if we expand this term, so that is omega n raised to L into omega n raised to n by 2. Let me write over here. Here we can represent this omega n L into omega n by 2. We can represent this addition omega n raised to L plus n by 2. So that is omega n raised to L into omega raised omega or W, whatever you consider, n by 2. Simply we have to remember this is a trivial factor. Omega n raised to L into omega n by 2. So here value of this n omega raised to n by 2, that is minus 1. Okay, so this term can be replaced with the minus 1. So here we replace this term with the minus 1. So what happened? that is equal to minus omega suffix n raised to L, where L is nothing but the integer. So this is nothing but it is known as a symmetry property of the Twiddle factor. So omega suffix n raised to L plus n by 2 is equal to minus omega suffix n raised to L, where L is nothing but integer. So this is nothing but here we replace this term with this value. Okay. Now we go for the second property, that is periodicity property of Twiddle factor. Periodicity property of Twiddle factor. Now here omega n raised to omega suffix n raised to L plus mn. So here if I expand this term, omega n raised to L into second term is omega m into n. Okay, now this m into n. So we can take this term as a omega n raised to n. That is a m times repetition of this. So omega m raised to n. So we, as per our calculation, this omega suffix n raised to n is equal to 1. So now we can replace this term with the value 1. With the value 1. So what we are written, omega n raised to L plus mn is equal to omega suffix n raised to L, where L and m both are integers. It's nothing but here it is replaced with 1. So your answer is omega n raised to L. So here value is 1 for this term. This is nothing but the periodicity property of Twiddle factor. Hope all you clear. Anybody have any doubt regarding this? First is we calculated these terms. Then we go for the symmetry property where we replace this n by 2 value with minus 1. So minus sign will be here. In second case, periodicity property, we taken the term omega suffix n raised to L plus mn is equal to omega suffix n raised to L, where L and m are integers. So here we replace this term with the value 1. So here we are getting the value omega suffix n raised to n. Okay, so this is about the properties of Twiddle factor. Now this we have to utilize for the calculation of DFT. When any sequence is given and we have to calculate the discrete Fourier transform for that, we can apply these properties. Okay, but another is when we go for the calculation of IDFT. Okay, let me move to the previous slides. Yeah. For the calculation of IDFT, we have to obtain the sequence from the given discrete transform. So x of n is equal to 1 by n sigma k is equal to 0 to n minus 1 x of k e raised to minus e raised to j 2 pi k by n into n. Here we are using the term minus over here for the DFT, but here the term is positive. Okay. So as your complex term is positive or negative, so it will affect only the imaginary part. Your real part remains same, only the imaginary part will be, sign of the imaginary part will be changed. So simply we can say that thing as a transpose. Okay, so suppose, just a second. Yeah. Here instead of using the omega n into the equation, we are using the omega n this. That is nothing but a complex conjugate operation. So when we are performing the complex conjugate operation, your real part remains same and the imaginary part, sign of the imaginary part will be changed. So when the calculation of IDFT using Twiddle factor, so instead of using direct Twiddle factor matrix, first we find out the complex conjugate or transpose of that, and then we multiply it with the given DFT sequence to obtain the input sequence x of n. Okay, so this is how we can obtain the IDFT. Okay, so this is how we can represent DFT and IDFT in the matrix form, how to utilize the Twiddle factor, and how to calculate the DFT with the help of Twiddle factor. And another is how to obtain the IDFT with the help of Twiddle factor matrix. Okay, all of you clear up to this? Okay. Now we move to the examples based on this dual factor matrix. All of you written all this. At present, as slides are not available, I suggest you to note down this equation which can be used for the solution of example. So better is you can write few of these equations, just the main DFT equation with you. Another is this dual factor matrix. You note down this matrix, and this is what you have to write at present for the solution of DFT. For IDFT, write down the equation of IDFT in the form of dual factor and this transpose of this matrix. Okay, so at least at present, note down this equation, first one, and then this. Please note down this, then we go for the solution of example. As you finish, please comment, then I start the example. Okay, as in the last lecture, I suggested you to rename your ID. I think a few of other faculties also suggested to you. So just first write down your ID and then your name as per your roll number. So it is easy for us to take the attendance. Okay, please let me know as you finish. Then we go for the solution of example. At least one or two we try to solve today. Okay, Jinendra, you are completed. Okay. I think all of you written. It's a very simple one. So I given around 5-7 minutes to write this. Okay, so now let us move to the next example based on this twiddle picture. Okay, so first is find the DFT of a given sequence. Find DFT of a given sequence x of n is equal to 2, 3, 4, 4. Here you add one comment in this example, that is find DFT for a given sequence x of n is equal to 2, 3, 4, 4 using matrix formulation. Using matrix formulation or using Twiddle factor method. Because sometime in title only this statement is given. Suppose this kind of statement is given, you have two options. Either you can solve using the previous method or you can utilize the Twiddle factor. Okay, but if it is specifically mentioned, then you have to go for the Twiddle factor. Okay, so find DFT for a given sequence x of n is equal to 2, 3, 4, 4. Okay, so here sequences 4-point sequence is given. You can calculate n is equal to 0, 1, 2, 3. So total 4 points are given. So we can say that this is nothing but it is a n point, or n means is equal to 4. So 4-point sequence is given and we have to calculate the DFT for this. So first step is we have to prepare the matrix formulation over here. So as I told you, here 4-point sequence. So we are getting the 4-point DFT. So that is x is equal to 0, x is equal to 1, x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3. And here this is nothing but your given sequence. Here this is a given sequence. We represent this sequence into the n cross 1 form. Similarly, we return the DFT again in the form of n cross 1 form. Here n is equal to 1, or sorry, n is equal to 4. So we are represent this into the 4 cross 1 form. So these both are as a x of k, sorry, x of k, capital X of k and small x of n. This is nothing but both are column vectors. Now this is the Twiddle factor matrix. So as we return, this is the n cross n matrix. N cross n. So here n is equal to 4. So here this is nothing but 4 cross 4 matrix. Okay. So as I told you, the initial values here in the last one we have discussed about this. Omega n is equal to 0. So here first row and this first column are replaced with the value 1. No need to go for the calculation of that. This is fixed in every case. First column and first row of the Twiddle factor matrix. For example, this is a 4 cross 4 Twiddle factor matrix. Suppose we go for 8 cross 8, 16 cross 16. Always first row, first column having value 1. Okay. Now we go for the second remaining values. So remaining values are here omega n1, omega n2 like this. So here we go for the fourth value omega, then omega 2, omega raised to 3, here omega raised to 2, omega raised to 4, omega raised to 6, omega raised to 3, omega raised to 6 and omega raised to 9. Here in this our value of k is equal to 1. So whatever values of n that are multiplied with 1 only. So initially 1, it is multiplied with 1, so omega 1. Second is omega 2 multiplied with 1, so omega 2, omega 3 multiplied with 1, omega 3. In the third row, it is multiplied with k is equal to 2. So what happened? N is equal, first n is equal to 1, k is equal to 2. So you are getting omega 2. N is equal to 2, k is equal to 2. Both are multiplied. So it is omega raised to 4, then omega raised to 6. Similarly, in the third case, here omega multiplied with 3 into 1. So first is omega raised to 3. Second case 2 into 3, 6. Third case 3 into 3, 9. So here simply you can say in the second row it is scaled by factor 1. So omega, omega 2, omega 3. In second it is scaled by factor. It is multiplied and you can say the scaled by factor 2 in the superscript. So that is 2, 4 and 6 notation you are getting. In third it is scaled by the factor 3. So omega 3, 6 and 9. Clear? So these are nothing but how you to write the Tweedle factor matrix. This is very important to solve this example. First is you have to write the DFT vector, column vector. That is, you must know this is the endpoint sequence. So you have to represent 4 cross 1 matrix or 4 cross 1 vector. X0, X1, X2, X3. Similarly, here 4-point sequence, that is 2, 3, 4. So here one thing I think I have missed over here. Here instead of equal, you have to write the multiply sign. These both are multiplied. Okay, to obtain the DFT as per our equation, this equation, x of n is equal to omega n into x of n. So by mistake here equal sign, but you have to consider this is a multiplication. So this is nothing but DFT sequence, 4-point DFT sequence. This is a Tweedle factor, and this is nothing but given sequence. Now we have to apply our properties to simplify or to find out the values of this. Okay, so first is omega n means this value. What about this value? This is nothing but if I'm taking omega n raised to 1, so it will represent e raised to minus 2 pi by n. Here n, this is a 4-point sequence, so e raised to minus 2 pi by 4. So that is nothing but e raised to minus pi by 2. So that is nothing but minus j. This term now will become minus j. Now second term, omega 2 or omega square, or you can say omega 2, I am telling omega 2. So that is nothing but if you apply the values omega 2. So that it will be, if you solve like this value will become minus j square or minus 1. J square means 1, so that is equal to minus 1. Sign is minus. Third one is omega 3. Omega 3 is minus j raised to 3. So that is equal to here j raised to 3. So it represents minus 1. Minus 1 into, sorry, minus j into minus, that represent the plus j. Now here we calculated up to 3 terms only because we have to apply the property of periodicity. Here we are having 4 terms only, omega 0, omega 1, omega 2 and omega 3. Remaining terms are repetition of that. So here as you are getting omega, omega 2, omega 3. Here omega 2, again you have to apply the value. Omega 3, again you have to apply the value, whatever you are getting. So omega is equal to minus j. Omega 2 is equal to minus 1. Omega 3 is equal to j. So these values are with you. Now you have to calculate the omega 4. Omega 4, now you have to apply the property, the periodicity property. In the periodicity property, omega p is nothing but omega p plus r. Means after every nth period, your matrix or your Tweedle factor repeats. So here omega 4 is nothing but omega 4 minus 4. So that is nothing but the same value, whatever you're getting omega 0, that you have to apply. So omega 4. So that is nothing but omega 4 minus 4. After every 4th repetition, you are coming at the first place. So that is omega 0. So here omega 4 having the value 1. Now the next is omega 6. So omega 6 is nothing but after 4th place, after 4 values, your Tweedle factor repeats. So omega 6 minus 4. So you are getting omega 2. So that is nothing but whatever value of omega 6, that will be same as omega 2. So omega 2 is equal to minus 1. So you have to apply minus 1. Omega 9. Omega 9 is omega 9 minus, here you written r into n. R means now here 9. So now your whatever your cycle you are taking, that is repeat 2 times because 4 plus 4, 8. Now you have to calculate the term 9. So that is a third repetition or n minus 1. So here r means repetition is 2. Here whatever r we are written, it is shows the repetition. And 4 is nothing but the your length of the sequence. So 9 minus 2 into 4. So that is again omega 1. So minus j. So if you apply the periodicity property, you will get the solution. And now your matrix will become like this. Just a second. Now here first term, as I told you, first column, first row, these values are fixed. Omega we have calculated minus j. Okay, we're done with this. Then omega 2, that is minus 1 applied. Omega 3, that is j. Again omega 2, omega 3, same values we applied at these places. Okay. Now omega 4, as we have calculated, omega 4 is nothing but omega 0. Omega 0 having value 1. So we can apply the value 1 over here. Then omega 6. Omega 6 is nothing but same as omega 2. So that is minus 1. We applied over here. Here omega 6, here omega 6. So it is also minus 1. Now last one is omega 9. Omega 9 is nothing but same value as omega 1. That is minus j. So that we have applied. So this is how we have to obtain the values of this twiddle matrix. Hope all of you are clear. This is very important to solve this example. After getting this value, the sum is very easy. You have to go for the matrix multiplication and find out the solution. Okay, so when you go for matrix multiplication of this n cross n matrix and this n cross 1 vector 2, 3, 4, 4, your answer will be 13 minus 2 plus j minus 1 minus 2 minus, which is nothing again n cross 1 column vector. Hope all of you are clear. If you are having any doubt, you can ask. Just a second, I continue with that sharing. Prior to that, just the time. All of you note down this example, entire example. And if you have any query, you can ask me in the comment box, or you can unmute your mic and you can ask. All of you clear about this example? Okay, Yashvi. Yes, sir. Anybody else? Jinendra. Okay. Okay. Priyanshi, Ajita. Okay. So all of you are getting. So please note down this example. Based on this, we go for the solution of next example. Okay. Today we finish with this example only. Please note down, and parallelly I am taking the attendance.